Good afternoon, everyone. Welcome to the Spring 2024 series of the Physics Colloquium. It is a pleasure today to introduce our speaker, Professor Philip Hopkins from Caltech. A brief bio about our speaker. He is a theoretical astrophysicist interested in a broad range of topics involving multiphysics and multiscale astrophysical problems, including the formation and evolution of galaxies, stars, supermassive black holes, and planets, the plasma physics of the interstellar and circum and intergalactic medium, turbulence, astrophysical dust grains and dusty plasmas, and relativistic cosmic rays, astrophysical probes of particle dark matter models and their phenomenology, numerical models of massively parallel simulations. Is there anything left in the field? Thank you. So this is indeed the breadth and depth of our speaker. He holds a PhD from Harvard University, where he worked with Lars Hörnqvist from 2004 to 8, and was a Miller and Einstein Fellow at UC Berkeley from 2008 to 2013, before moving to Caltech as a faculty member, where he is currently the Ira S. Bowen Professor of Physics, a Simons Investigator, and a recent recipient of the American Astronomical Society's High Energy Astrophysics Mid-Career Award. Please join me in welcoming our speaker.
Thank you. Thank you very much, everyone, for coming out. It's great to see so many people, and I hope that it's great to also be back here. I have to leave tomorrow, but I will hopefully be back soon. So hopefully, many of you I can chat to in the future about some of these other topics that I'm not going to be able to talk about today. It being one talk and not like 10 talks, I can't talk about even a fraction of some of the things that we're working on in our group. I do want to, advertise a few other big topics if you're interested in them, to reach out to me about if you wanted to talk more. We've got a group of current and former students working on topics like star formation, galaxy formation, cosmic rays, and the plasma physics of how high energy particles interact on sort of plasma scales. In diffuse plasmas, dust and particulate dynamics, both relevant for things like planet formation, but also how different plasmas behave under different conditions, especially highly irradiated ones, where dust can be the primary source of opacity and interactions with the radiation field, and sort of astrophysical tests of dark matter and how we can test and constrain different particle dark matter models through the astrophysics sector. And these are just some highlights of students and postdocs working in these areas that I want to advertise. Many of these people are on the job market, so hire them. They're all amazing. I wish I could give a colloquium about each of these topics, but ask me if you want to know more. But today, I'm going to focus on our work on supermassive black holes. And even within that, I'm going to have to focus a little bit because there's so many questions. But I want to introduce the subject a little bit first, because I know this is a mixed audience, so not all of you might be convinced that this is a super exciting area to study, although maybe there's a bias for those of you who actually bothered to come to this talk. So what are supermassive black holes, and why do we care about them astrophysically? Well, they are these giant black holes that are observed to sit at the centers of galaxies, both active galaxies, where that black hole is accreting or swallowing material at a rapid rate, or inactive galaxies, like the center of our galaxy. So this is a map of the orbits of stars in the center of our galaxy. This is what the Nobel Prize was recently awarded to Andrea Ghez and Reinhard Genzel and their teams for, is basically proving the existence of a supermassive compact object that we don't have any candidate object other than a black hole that could possibly be this thing at the center of the potential galaxy. Oh, the lights? Okay, thank you. So we see these in the centers of galaxies, and almost all massive galaxies have these black holes at the center of them. But we also see them lighting up. So I said when they're active, they can be accreting. So these things, when they're swallowing huge amounts of gas, can shine as quasars, the most energetic sources in the universe, the most sustained luminous sources in the universe, the most luminous sustained sources, as well as other related things that we call Seyfert's radio galaxies. There's a whole zoology of similar things. This is a famous galaxy where this is the sort of normal galaxy, and these are jets of material that is nearly falling into the black hole before being launched back out at relativistic speeds, propagating all the way into the intergalactic medium around the galaxy. Of course, we can also image the very small scales around black holes. This is one of the famous images from the Event Horizon Telescope of the material swirling right around the event horizon at the center of this galaxy, where they've imaged two black holes, one at the center of a nearby galaxy, M87, and one at the center of our galaxy. And this is the material right around there. But this image can already highlight one of the things I'm going to come back to over and over again as the challenge and the reason for the subtitle of my talk, which is, like so many things in astrophysics, the challenge here is the enormous scale disparity of these problems. So this event horizon, where most of the energy is being released, so material works its way all the way from out here into this galaxy and is eventually swallowed into the event horizon. But some of that material, before it's swallowed, as it's spinning around at nearly the speed of light, is shocking or generating friction with other materials swirling around that black hole, and that's generating a tremendous amount of radiation that we can observe as these luminous quasars. But the scale here, where most of the energy is being released, is something like in AU, an astronomical unit, about 10 to the 13 centimeters, and yet we see the macroscopic effects of these accreting black holes propagate out to something like at least megaparsec scales, 10 to the 24 centimeters or so. So we've got a sort of 10 to the 10, 10 to the 11 range in the scales that we need to couple strongly in this problem, basically. So that's challenging, and again, I'll come back to that. But why do we care? Well, I mean, those are interesting things I already just showed you that we care about for their own sake. But these black holes are also interesting in a number of other respects. So they're valuable probes and test beds for high-energy astrophysics. They're laboratories. It's worth noting, again, for those who aren't as familiar with this, that black holes are nature's most efficient mechanism for turning mass into energy, for extracting mc squared. The only more efficient mechanism is matter-antimatter direct annihilation, but there's not a lot of antimatter lying around, and this isn't to talk about baryogenesis or anything like that. So the next most efficient thing that nature definitely does make are black holes, and you can release more than 10% of mc squared of material as it falls into a black hole in the form of, say, radiation and other energy that escapes. They also are central to our understanding of galaxy and star formation. So it's now widely accepted that black holes and galaxies co-evolve. So there are these very famous correlations between the mass of these supermassive black holes in galaxies and the mass of their host galaxy. This is just a sort of heuristic illustration of this in different galaxy types, where a part in a few hundred or a part in 1,000 of the galaxy mass is locked in the mass of that supermassive black hole. So that's not a huge fraction of the galaxy mass, but if you ask energetically how important is the black hole, I'll come back to this point, it can be hugely important, because if you ask how much energy was liberated in forming that, because of this enormous efficiency, it can easily be much more than the gravitational binding energy that's actually holding all the matter in the galaxy together that was liberated in this black hole's formation. Plus, this correlation appears to exist across a lot of cosmic time, telling you that somehow galaxies and their black holes grow together. And there's a lot of this phenomena that we call feedback, where that radiation emitted by the black hole or other energy coming out from the accretion near the black hole can act back on the galaxy around it, blowing material out of the galaxy, for example, and shutting down subsequent generations of new stars forming, that kind of thing. Of course, black holes have also come into great prominence in the last few years as both tests of gravity, in, for example, the galactic center or with EHT imaging, as well as a key point of multi-messenger astrophysics. So these supermassive black holes are not what we're seeing in LIGO, for example, but they are what we're measuring in gravitational wave emission, we think, with pulsar timing, although there's still some controversy about that. And they're what future instruments, gravitational wave instruments like LISA, are designed in large part to detect, are the interactions of some of these supermassive black holes. They're also multi-messenger in the, of course, they're emitting radiation, as I already mentioned, and they're among also, in addition to being incredibly energetic, they're some of the broadest spectrum known types of sources in the universe. They emit comparable amounts of energy over a ridiculous wavelength range, from gamma rays all the way to the longest wavelength radio emission. And they also generate things like ultra-high energy cosmic rays and neutrinos. So, for example, other than the infamous or famous neutron star merger, where we detected the gravitational waves and the light, The only other argued confirmed multi-messenger sources where we detected two different kinds of messengers from the same thing were supermassive black holes. So for example, there's claims that we've detected a simultaneous arrival of neutrinos and gamma rays from blazars, which are a type of accreting supermassive black hole. There's lots of reasons to study these, but what's the problem? Why don't we fully understand them? Well, as I said, the problem is that these are incredibly multi-scale systems where the small and large scales are strongly coupled, but they're also multi-physics systems intrinsically. So if you're a string theorist who wants clean, elegant physics where I can write down an equation that is the equation, you can stop watching now, because none of this is going to be that. This is horrible, messy astrophysics, right, where lots of different things are happening simultaneously, and that's, for me, the fun part, because all sorts of wild new phenomenology can emerge from those mixed physics. So just some of the physics that we know are important are things like radiation, magnetic fields, gravity, thermo-chemistry, and star and galaxy formation as gas goes in and out of these black holes. And that leaves a lot of those are hard to model and understand, let alone across this range of scales, so it leaves some very basic questions open. So some of the really big picture questions that the community does not have agreed upon answers yet are, where do these supermassive black holes come from? Often phrased as, what are the seeds of these supermassive black holes? How do they grow? How do they accrete? How does it depend on their environments? When do they accrete? And what do they do to their surroundings, which we often call feedback? How do they affect the galaxies and the environments in which they live? So these are pretty zeroth order, and my talk is going to be divided into 3 sections, most of it on this middle section, although I could give a whole talk about any of these other pieces, about recent work trying to address and potentially overturn some pieces of conventional wisdom in each of these areas, where I think in the last few years we've come to appreciate that things are maybe a little different, or in some cases a little more interesting than what we used to think, or for many decades in some cases. So let's start with the seeds question. How did these black holes get here? So a couple pieces of conventional wisdom. So this is a little bit of inside jargon, but I'll try and explain it. So there have been a number of detections, increasingly, every time we build new telescopes or new instruments that can probe it, we find supermassive black holes at even earlier cosmic epochs, when the universe was even younger, that are incredibly massive. So I think most people would agree there's definitely things that are in the many billions of times the mass of the sun, many billions of solar mass black holes already around at a redshift of 7 or 8 or so, and there's some much more tentative detections when the universe is only a couple 100 million years old, and some much more tentative detections at, say, a Z of 13 or so that are still maybe more controversial, I would say. But either way, these things exist, and one of the commonly claimed things is that these favor what are called direct collapse models, models where somehow the universe doesn't make a small seed that grows up to a big black hole, it just somehow directly makes the big black hole. It skips the intermediate stage because there's just not enough time, and I'll come back to that in a moment. Another piece of conventional wisdom is that however you form these things, these black holes, these smaller black holes, will efficiently sink into galaxy centers by a process called dynamical friction. Don't worry about that if you're not familiar with what that is. It's basically scattering via gravitational effects off of other stuff in the galaxy. And then once they're at the galaxy center, they efficiently grow. And these form a lot of the basis for a lot of our intuition, I would argue. But I would argue that both of these are probably incorrect. So let's first talk about this direct collapse or seeds question. This is an explanation of how this is a toy illustration or function for how a black hole would grow in time, or redshift z. So there's, if you assume you need to grow a black hole fast, the problem is that there's a sort of speed limit that nature imposes naively, which is called the Eddington limit. And again, I think most astronomers are familiar with this, but if you're not, essentially you say, okay, if something has some mass m, and I try and take if I imagine I have some test particle electron around that object, there's gm over r squared pulling it in towards the center via gravity, but there's some flux of light, L over r squared, coming back out, and that will imply some Thomson scattering of that electron from those photons that will push it back out. And the Eddington limit is when that radiation pressure exceeds the gravitational pressure. And that says you can't be shining brighter than this limit. And if you convert a fixed fraction of your mass accreted into energy, then your luminosity is proportional to the rate at which you're growing. So it's a speed limit on how fast you can accrete, if you make that assumption. So if you accrete at some fraction of the Eddington limit, which is this lambda Eddington, then you grow exponentially with an e-folding time of 50 million years or so. This F duty is the fraction of the time that you're on. And so the problem fundamentally with these very high redshift black holes is that there's not a lot of time. And the theories of how you could do this basically since the 70s pointed out, or even earlier, that you have sort of two choices. You can either, if you want to make a really big black hole at some early time, you can either make this prefactor very big, which is where you skip the small seed and directly make a very massive black hole. And there's various exotic ways you can do this. You can have a cloud of gas, contract somehow. It takes a lot of fine-tuning in practice, avoid it splitting into, breaking up, fragmenting into individual stars, so that it can coherently form what we call a quasi-star, like a million-plus solar mass star, that very quickly, unstably collapses on itself into a black hole. Or you can break the Eddington limit. And even if you're not familiar with the Eddington limit, from my simple description, you can probably already imagine ways you could break the Eddington limit. It assumes things like spherical symmetry, like that you're optically thin to the radiation that's coming out, that you're Compton thin, that you're ionized, that your opacity is essentially free electron opacity, et cetera. There's a number of assumptions implicit in that limit. But more importantly, the point is, if you assume that you're Eddington limited, but you start from a big seed, the problem is, this is the term inside the exponential, right? This is the term outside the exponential. So making this bigger doesn't help you nearly as much as making this bigger, just because this is inside the exponential, right? So the problem is, if you start from a million solar mass quasi-star, of which, let's say, be generous, you turn 10% of it into a final black hole, which is these days probably an optimistic estimate, it'll still take you, if you accrete at the Eddington limit, almost 500 million years to get to like 10 to the 9 solar masses, to several billion solar masses. And if you're only on for a few percent of the time, which is many people would consider a more realistic estimate of how often these black holes are accreting, it's going to take you tens of billions of years. Whereas if you started from a normal black hole, here let's be generous and say normal goes up to 100 solar masses, because we know those exist and can be made by some combination of stellar evolution processes and mergers of normal black holes from individual stars, it takes you about twice as long to grow. On the other hand, let's assume that I allow what's called hyper-Eddington accretion, which is, let's take a toy model where 1% of the time I go way past the Eddington limit and I accreted 1,000 times the Eddington limit. I bypass it completely. Well, then it takes me about 50 million years to do this. So again, this is just making the really obvious mathematical point. I apologize if I'm spending too much time on it, but it's a simple point. And I would actually argue that the earlier and earlier we detect these black holes, the more and more it points to the fact that nature grossly violates the Eddington limit. Because even with the current supermassive black holes that we're detecting at early times, even if you assume the most optimistic models for how big this prefactor can get, we're starting to push into this still needs this lambda to be bigger than 1 in this exponential to make them in time for us to see them. So this is something that we've been doing a lot of experiments on. I'll talk a little more about the accretion physics that can enable this. But I just want to advertise a student, Yanlong Shi, in collaboration with a postdoc, Kyle Kremer, have done a number of experiments for even very small seeds in dense environments that represent very high redshift galaxies to show that black holes can indeed capture gas at rates up to sort of 1,000 times the Eddington limit. It takes special conditions. They have to get lucky. It doesn't happen all the time. It doesn't happen to every little black hole wandering around, and it shouldn't, because there aren't that many gigantic black holes wandering around. But it's also not that implausible. It's basically you have a very dense molecular cloud, the kind of thing you might see in starburst nuclei, what we call ULERGs or other merging galaxies. Typical densities in those clouds, you have about a 1% chance of your black hole just having all the stars align where there's some super dense shock of gas that the black hole just happens to line up with in its random motion, so that there's very little relative velocity, and it's sitting right on top of this high density. That's just one way this can happen. But the point is, order 10 to the minus 3, 10 to the minus 2% of the time, when you have these extreme conditions, you can get that to happen, and then this black hole can just go wild and accrete as much as it wants to in a very, very short amount of time. Now, we've also worked on some more extreme models. So Yanlong also worked on, can you form a very massive black hole by things like runaway merging stars in the centers of a dense star cluster, where stars would sort of slam into each other and can, under the right conditions, trigger a runaway. What he actually found in those situations was that you still get pretty small seeds. This runaway, for various reasons, it's very difficult, he found, to get this to be more than a few hundred solar masses, final mass of the black hole. With a student at Washington and another former student, Jacob Shen, we worked on some exotic dark matter models where if you really want to give me, let me get exotic and invent new degrees of freedom, then I can give you some exotic dark matter models that might form these black holes in the centers of early forming dark matter halos. I mainly encouraged them to work on this project because I was convinced that any model that would make a reasonable black hole at these early times would make way too many black holes everywhere and be ruled out immediately. And they actually found a quite reasonable parameter space where they could make the observed ones and not overpredict everything. So kind of a neat result. I'm not going to bet on that one, though, but it's fun to think about. But as we were doing these experiments on high redshift early black holes, we also found another problem that arose. And that's why I'm showing you this movie. So this movie is a modern simulation of how a galaxy forms over cosmic time, looking at the stars and gas. And this is another thing where our conventional wisdom has changed a lot in the last decade or so. And it's become clear, both observationally and theoretically, that there are sort of distinct stages of galaxy formation in the life of a massive galaxy, where most massive galaxies at early cosmic epochs, high redshift labeled here, are very chaotic. They go through this incredibly clumpy, irregular, rapid accreting, feedback-dominated phase where they're blowing stuff out, and I'll just reset the movie a second so you can see just how chaotic this early phase is, where everything's a complete mess. So there's galactic winds, giant inflows of gas fall into the galaxy, trigger enormous amounts of star formation, supernovae explode in huge numbers, they launch material far out of the galaxy, et cetera. And this galaxy is a complete mess, okay? Dynamically and in every other possible way. And it's not until quite late times that the galaxy sort of dynamically settles. In fact, that's the term increasingly people are using, is sort of settling of the galaxy at some transition period where it starts to form a more regular galactic disk. And the cartoon, if you've taken a galaxies class or read a galaxies textbook, the cartoon picture of galaxy formation is always that there's sort of a hot gaseous halo that cools, conserving angular momentum to form a rapidly rotating disk in the center. And that does work at late times in this image, but it's not a very good description at those early times during all that chaos. And it's only, there's the last burp of this galaxy. It's triggered by a merger here. And then after this, it builds up a disk steadily all the way to present day, basically. And the disk just gets, the gaseous and stellar disks just get bigger and bigger and thinner as this thing continues to evolve. And this has a bunch of consequences. One I'll just briefly mention as a sort of side advertisement is this may be very important for some of the puzzles that James Webb has been posing. You might have heard that they're seeing too many massive galaxies at early times, and this is a problem for cosmology, but some former students, Jacob Shen and Jason Sun, have written a couple of papers pointing out that there are many effects that can boost the brightness of these galaxies in the UV compared to what's usually assumed. This is just a toy illustration from Jacob's paper. You have some reference model with observations way up here. This is what's usually meant in these papers when they're like, there's too many massive galaxies at high redshifts. They're comparing to some specific reference model that assumes things like the relation between stellar mass and halo mass and UV luminosity is fixed over cosmic time. There's systematic evolution effects where star formation is more efficient at early times. There's various observational biases, which are a small effect here. These are all effects and how they affect this. There's metallicity or abundance effects. There's contamination from the AGN, which is why this is appearing briefly even in this talk, because we wanted to look at how much were the luminosities of the AGN affecting this, and we found very little. But what we actually found was that this chaotic period, where there's lots of very rapid fluctuations in the brightness and the star formation rates of the galaxy, has a huge effect on this. Because basically, for a small mass, if you're wildly fluctuating up and down, right, if you're way out on the tail, at the very bright end of a steeply falling number versus luminosity function, then convolving this line on the left with scatter will massively boost this end, right? And that's true for any, this is just a basic statistical fact, and that's all the argument in these papers fundamentally is. But they showed very nicely, and this is the more quantitative version of their papers, how this sort of boosts things and can potentially explain things. And then related work by many students and postdocs as part of our FIRE or galaxy formation collaboration has shown that this also plays a key role in explaining a lot of the structural properties of galaxies today. I could give a whole colloquium on this. Those are all simulated galaxies. This is a bit of a brag slide just because of how pretty all those galaxies are. But what I showed you in that movie and was trying to explain is shown quantitatively here in this plot from NAU, which is showing as the star formation calms down at late times, you see this transition from it going all over the place in that chaotic period to calm. You also see a real transition in where the stars that formed the present-day disk form. But this all, come back to black holes, has a really important implication. Because our picture of how black holes stay in galaxies and accrete is always that gas comes into the galaxy, gradually will lose angular momentum and work its way closer and closer to the center of the galaxy. Some of it will get lost to star formation, some blown out by winds, but some of it will gradually lose angular momentum and get further and further down in the galactic potential well as it loses energy and angular momentum. And the angular momentum is really the fundamental problem. Gas can lose energy relatively efficiently by radiating energy away, but the angular momentum problem, gas in the intergalactic medium has to lose something like has to decrease its angular momentum by something like 9 orders of magnitude before it can be accreted by a black hole. And so that's our cartoon picture, is that this sort of gradually happens on multiple scales as you go down. But how does that work if your galaxy is going through this incredibly chaotic dynamics phase? This is not a system in which you can even define an angular momentum vector, right? Because it is not axisymmetric, let alone point to there is the center towards which the black hole will clearly net migrate as, or the gas, if the black hole got to the center, would net migrate. So this whole picture really only works once the galaxy has sort of calmed and stabilized. And this is a challenge in all the models. So at late times, when your galaxy is beautifully ordered, this all works. The black hole can sink to the center, be anchored there, and gas can flow in towards it. But at these earlier times, if you want to have black holes be active in the early universe, you need to do something different. Either you need to have them be anchored by something, right? Your black holes, if they're free wandering in this chaotic phase, the truth is dynamically, 3-body and higher n-body interactions are just going to launch those black holes out of the galaxy. You actually see this. There's, it's hard to see in this particular movie. I'll show it if anybody's interested. There's a bunch of other red X's here, which are all the black holes that get launched out of this galaxy just kinematically at earlier times. Most of them don't survive to present day, basically, in the galaxy during this, if they formed during this chaotic period, basically. So you need to anchor them. One way to do that is to maybe say that they preferentially form in some very much more massive things like dense star clusters or something like that, which isn't an implausible argument, but it does put more constraints on your formation model. Another is to say that maybe they only really start growing once this settling starts happening, but then you're really even more limited in time, right? Then you've just narrowed your time window to grow these things a lot more than we already were working with. So I'm not presenting a solution here. I'm presenting this problem has only gotten worse with time, basically, is my argument. But that said, let's come back to these points of conventional wisdom. So is it true that these high redshift observations say that you have to make a black hole massive to begin with? No, I would say they require that it grows incredibly rapidly, and that once it does, the seed masses are sort of forgotten. And do black holes and the gas very efficiently sink? Well, they can't sink until these sort of well-defined centers form. All right, so let's move from that to black hole growth. That's a good transition point to talk more about how these black holes grow, okay? So black hole growth. let's assume that we have now a settled down galaxy, just to make our lives easier, that the galaxy's settled down a bit and that there is some supermassive black hole at its center, but it still is growing a lot. It's still shining as a quasar. How does that happen? Well, one of the challenges that's been around for decades is that there's a widespread argument that if you try to funnel gas down from galactic scales, that at small enough scales, what we call the black hole radius of influence, this is just where the black hole starts to dominate the potential, that inflows become inefficient. And there's a simple argument for this, which is simply that in the center, once the black hole dominates the potential, it's a Keplerian potential. So what are orbits in a Keplerian potential? They're just closed ellipses, right? So it's perfectly stable for you to just sit there forever. And a lot of things that can happen on galactic scales, like certain types of instabilities like galactic bars and things like that, get shut down at those scales because the orbits don't permit them. The structure of the gravitational potential doesn't permit those kinds of structures to form in the same way. I could go into a lot more detail on that, but I'll just touch on it briefly. Another problem is that if you take traditional models for how black holes grow and how they're fueled, if you try to feed the black hole at super Eddington rates, it doesn't work. If you try to feed the black hole above the Eddington limit, this is part of the reason why theorists maybe were biased against the Eddington limit, even though it wasn't that hard to come up with ways around it, was that if you take the standard accretion disk models and feed it faster than Eddington, or even feed it close to Eddington, the disk is wildly gravitationally unstable and fragments under its own self-gravity into little chunks that turn into stars or something, but they don't coherently orbit and spin down and feed the black hole. And as I mentioned the traditional accretion disk model, this is implicit on the idea that the accretion disk, the conventional wisdom, is that it's something like what we'd call the Shakur-Sunyaev or alpha disk models. I don't care about the specific. This is a particularly seminal paper from the early 70s in astrophysics, but fundamentally the assumption that this and many other, almost all classes of accretion disk models, with a couple notable exceptions that I'll mention, make is that the magnetic fields are relatively weak in the accretion, in the swirling disk of material accreting onto the black hole. Okay? And that, I'll show in a moment, leads to some really drastic consequences. So we want to study this and how black holes get their gas. Now, when you ask how do black holes get their gas, which is something that, I mean, I've written papers with literally this as their title, how do black holes get their gas? It's a bit of an ill-defined question, because if you're asking, how does a proton get from the intergalactic medium in the cosmic web into the event horizon of a black hole, there's this enormous scale hierarchy, as I mentioned, and there's different physics happening on this range of scales. This is just an illustration of gas and starlight on a range of physical scales from megaparsecs to milliparsecs, with sort of names we sometimes give to these different sort of orders of magnitude in scale. The intergalactic medium, the black hole radius of influence, or the torus around the black hole, the accretion disk scales, et cetera. So for a number of years, we've been interested in this problem, and certainly we're not the only group who's been working on this, but I was starting to work on this in my PhD thesis and in my time as a postdoc at Berkeley. I think that was actually when I wrote the paper with this as its title, actually. We looked at mostly the large scales. So from sort of the intergalactic medium, you've got things like the simulation I showed before, where there are these cosmic web filaments feeding galaxies with flows that have very little angular momentum initially on cosmic scales, but then they get wrapped up around galaxies. And then in a galactic disk, you can have things like collisions between galaxies. Sorry, this isn't playing, but this is an animation of a collision between two galaxies, galaxy mergers, or I mentioned these spiral and bar instabilities in galaxies, these gravitational instabilities that form these large non-axisymmetric structures in galaxies that introduce torques into the orbits of the gas and cause it to lose angular momentum and spiral in. And then the thing I worked on a lot as a postdoc, but again, other people have been working on, and the ideas go back decades, is that you can have a hierarchy of these types of instabilities and structures. So this is sometimes called bars within bars. Elliot Quadert and I tried to be more agnostic and call it stuff within stuff, because many of these things don't look like bars, actually. But you just get a hierarchy of different instabilities down to small scales. And that can go right through this radius where the potential becomes approximately Keplerian, because while I said some of these instabilities get shut down, something that was known, but I think not appreciated in this community in particular, is that some of these instabilities are not shut down in a Keplerian potential. Certain types of for those in the field, certain types of m=1 modes can propagate perfectly well through into a Keplerian potential and arbitrarily far down in the disk in a Keplerian potential, especially in these types of situations where you have a disk of mixed stars and gas. And I'll come back to the importance of that in a moment. But then there's still this sort of gap where we've had very little work in the last few decades. So most of this work and all these movies here was from groups and simulations and theorists who were used to thinking about things like the interstellar medium and galaxies and star formation. And then there's sort of a gap in scales, and then you got a completely separate group of simulations of people who like to think about accretion disks in strong spacetimes around, strongly curved spacetimes right around black holes. And the scales here don't overlap, and the physics here don't overlap. The physics approximations that you can get away with here versus the physics you have to care about here are very different from the physics approximations that you have to care about here. An obvious example is here you need GR if you're close enough to the black hole. Up here, I don't care about GR. Those effects are incredibly negligible. Here, I need to care about star formation, because that's happening everywhere and could deplete all the mass that would feed the black hole. Here, nothing's forming stars this close to the black hole. So you didn't even have the same codes simulating these problems. You had wildly different codes simulating these different scales with totally different approximations being made. And there was literally no code in the field until recently that was sort of being simultaneously used really for both of these, or at least no off-the-shelf code. There were custom versions of codes like Flash that had been evolved for one area or the other. And that's part of the challenge here on the multi-physics side. So what we've really been trying to do is sort of go further to unite these scales. So just briefly, work by Daniel Engels-Alcazar, who's a collaborator at UConn, and some students and postdocs working with him, including Jonathan Mercedes-Feliz and Rachel Cochran, has sort of more self-consistently pushed this by, in a single simulation, following the gas at higher and higher resolutions as it falls in. So they start from a very large cosmological simulation where you're evolving a whole universe, basically in a box. But as material falls in around a galaxy, you zoom in, you refine, you increase your resolution as that material goes in. And as that material goes further into the galaxy around the black hole, you keep improving your resolution further and further. And in these simulations, they were able to follow gas down to about a fraction of a parsec around the black hole, and show that at a number of different stages, they picked different times to sort of zoom in on this process. The trade-off when you do this zoom in is your time steps and the amount of computational expense to evolve those inner regions gets higher and higher. So you can't evolve this inner region for 10 billion years because the dynamical times might turn into hours or even minutes in these regions. But you can evolve it for long enough for it to reach some equilibrium given its outer boundary conditions. And they chose a few different times to zoom in and showed that you could get very high accretion rates at some times into these central regions, like quasars, multiple solar masses a year falling into the supermassive black hole. And that generically, on these larger scales, this was the result of these hybrid star-gas disks. So this is an illustration from a larger scale, galaxy scale simulation, but it's the same physics. The idea is that when you have these multi-component disks where you've got a mix of stars and gas swirling around, these are very interesting from a dynamics point of view because the stars are effectively collisionless, meaning that they just go past each other. They don't have strong star-star interactions, whereas the gas is collisional. It has pressure forces. It's in the fluid limit. And that means that these perturbations move differently and respond differently to their gravity, and they can torque very strongly on each other, basically. And this is part of what allows these perturbations to remain strong, even as they propagate in towards the black hole. But at some point, star formation has to stop in order to keep feeding the black hole and just to match what we observe. And we need to actually get down to the accretion disk. So the next step in this program is what we've been working on for the last few years, and we just published the very first results. So this is from a paper earlier this year, a few months ago, called Forged in Fire, because it combines the physics from two big projects, StarForge and FIRE, simulating very small scales in the interstellar medium and very large. And what we did was just keep zooming in all the way down. So you're falling in at much faster than c, around a massive galaxy at around a redshift of 4.5. It's on large scales a messy merging system with multiple giant complexes of merging galaxies and molecular clouds whizzing around. One giant molecular cloud complex of about 100 million solar masses whizzes by a pre-existing 10 million solar mass supermassive black hole and gets tidally torn apart. You get a big tidal tail that falls in, wraps around the black hole, circularizes and forms this accretion disk, which keeps going all the way in. And this simulation went down to about 80 AU, or about 300 times the Schwarzschild radius of the black hole. We have a follow-up simulation that refines even further that goes down to 30 times the Schwarzschild radius of the black hole, basically the limit where these simulations don't have general relativity, and we can't keep going because you need the GR to keep doing it. But these aren't just impressive from a resolution point of view. You know, this is the first time we've been able to cross such a wide range of scales, but really the important thing is the physics. So I mentioned that earlier. The key is that we've built a set of physics modules that can simultaneously handle these different regimes. So that means doing all the thermochemistry that might be relevant over this incredibly wide dynamic range of densities and scales. If you want to talk to me about opacity tables, they're a nightmare, but I've got a ton of compilations of them that we did for this. With multi-band radiation transport, because you've got radiation in very different wavelengths being important at some of the different scales in this problem. Magnetic fields being treated self-consistently, self-gravity, of course, models and detailed models for star formation that at high resolution can resolve the evolution of individual stars in this medium, the formation and evolution of individual stars. And this gives you this incredible hierarchy of scales. This image I showed earlier of the gas was actually from this simulation, showing this sort of milliparsec to megaparsec range of scales. And we were ready to just say, amazing, we did it. You know, there was an accretion disk. That was our goal when we started this project. And we were pretty happy that we got that. But the thing that we didn't expect, that I'm going to spend the rest of this talk about in what time I have left, is that this black hole is, this accretion disk, sorry, is qualitatively different from what the decades-old standard theoretical model predicts it should be like. And the fundamental way in which it's different is that it's incredibly strongly magnetized and turbulent compared to what the standard model predicts. These are just some illustrations of the magnetic field lines. This is showing how the magnetic field strength depends on distance from the black hole, from megaparsec scales to milliparsec scales, where you see it sort of amplifies continuously from the sort of intergalactic medium all the way up. So you start from sort of nano-Gauss fields in the intergalactic medium to micro-Gauss fields in the interstellar medium, all the way to kilogauss fields in the inner part of the accretion disk. And actually, the magnetic fields, as I'll show in a moment, are just primarily being amplified by flux freezing in these inner regions. And we'll come back to that in a moment. But they play a really crucial role. They're not just strong in a measurable sense. The ratio of magnetic pressure to thermal pressure can be 10,000 easily in these disks, which is, or a plasma beta for those of you who are more used to that. Plasma physics terminology can be as low as 10 to the minus 4, even 10 to the minus 6 in the disk, which is incredibly strongly magnetized by the standards of most astrophysical systems. And it plays a really key role. So this is an example of the inflow and outflow rates versus distance. So this black line, pay attention to, is the inflow rate. This red dotted line, for example, is the rate at which gas is being turned into stars as it gets towards the black hole. And you can see at some point these magnetic fields prevent gas from collapsing on its own self-gravity and shut down star formation in these inner regions at sort of sub-parsec scales and allow inflow to continue unabated. And there's a little bit of outflow, but not a lot. This is just showing the inflow rate versus time to show it's fairly stable. But what happens if we, this is just showing the stresses. I won't spend too much time on that. Sorry, I skipped the key part there. But what happens if we remove the magnetic fields? I'll come back to this point. Just look at the right plot here. Now suddenly, the inflow rate in the very center drops precipitously. This little weird bump where inflow and outflow are equal is actually a single clump that's in a sort of eccentric orbit, basically, going around the disk. And the star formation rate is like 100 times higher, at least, because the gas can run away and fragment. So I'm going to talk more about this disk in the next 10 minutes, or 5 minutes. But the point is that these fueling from galactic scales can be extremely efficient, and that it can enable super Eddington fueling This disk is accreting at about 100 times the Eddington limit, I should note. But that's in part critically because the disk is magnetically dominated. So why are these disks magnetically dominated, and why do you care? Let me end the talk by talking about this. So I want to set this up pedagogically. So the conventional wisdom, or the traditional accretion disk model, says, okay, assume we got a black hole and some cloud of gas, and that the magnetic fields are weak. Okay, so it's thermal pressure dominated. Either we assume that the magnetic fields are initially just trace, so they're very small, or you can assume that it's threaded by some poloidal or vertical field, okay? And this might be a reasonable assumption around a star, where the field is dominated by some dipolar field of the star, or a neutron star, for example. I'll come back to the point that around a supermassive black hole, I don't think this is a reasonable assumption. But in this case, even if these fields are strong, if they're vertical, they can't resist gravity pulling the gas down. So gravity is going to compress the gas into the midplane around the black hole. This gas is orbiting around out of the plane of the screen. So the gas is going to collapse to a very thin disk, and it's going to get denser and denser until its thermal pressure is able to resist further collapse, basically. So thermal pressure eventually balances gravity, and you have an enormous thermal pressure in a very thin disk. The aspect ratio of these disks is predicted to be something like a part in 1,000, okay? The scale height relative to their radius, covering factor of the sky. Now, once you have this enormous thermal pressure, there's still nothing to give you strong stresses or torques in the disk. So how do you do that? Well, we believe that instabilities like the magneto-rotational instability develop a small amount of turbulence, a turbulent magnetic field and velocity field in the midplane, in some thin midplane layer of the disk that gives you an effective stress that acts like an effective viscosity in the disk. That's usually parameterized by this alpha fudge parameter, which is just this square of the velocities. And that's very small, but this little midplane layer generates that and is able to migrate inwards. Now, it's worth noting, even though this is weak fractionally, because we let the disk collapse to such high densities and such thin heights, the thermal pressure is so enormous that in order to even get a small value of alpha of 0.01, say, you actually need an extremely strong value of B in absolute units. Now, B is actually bigger in the prediction from these disks than it is in our magnetically dominated disks, because it has to fight against this incredibly strong thermal midplane pressure. I'll come back to that in a second. Now then, that eventually causes the disk to sort of viscously lose angular momentum and spread inwards and accrete onto the black hole. Now this has all sorts of problems that have been known for decades. I'll just briefly mention them. As I mentioned earlier, it's gravitationally wildly unstable. The Tourmaire Q parameter in the outer disk is less than 10 to the minus 6 or something for those who know this field. It's also got other instabilities that aren't seen. It has these thermal and viscous instabilities at high accretion rates, which would cause these sorts of global flashes of the accretion disk that we don't ever observe. It's well known for decades it predicts the wrong spectrum. The spectral model that this predicts is just wrong. It predicts the wrong effective temperature, the wrong spectral slopes, the wrong EUV and soft X-ray components. Microlensing observations show that the disks are predicted to be much too compact. There's a number of different problems. And there's a whole ecosystem that we know must exist around black holes that cannot be part of this disk if this is the right accretion story in the disk. So there's all these things. This is more for people who think about AGN. There's things that we know exist, like a corona, a broadline region, a dusty torus. These are regions where we see different emission lines and absorption features and things like that associated with it. But you can show that the thermal structure of this disk and its pressure structure makes it impossible for the kind of absorbers and emitters that need to exist in the broadline region to be part of that disk if the disk is thermal pressure dominated. So it has to be, it's not that they can't exist at all, it's that this broadline region, this torus, this corona all have to be separate things that are somehow hovering above the disk, basically, in the classic model. And that's how they've been modeled for decades, is something else makes this, something else makes this, something else makes this, that all kind of float above the accretion disk. But this is a problem where boundary conditions really matter. And that initial starting point is not a good one, I will argue. So imagine we have our galactic interstellar medium and some radius where the black hole dominates the potential. This is now looking sort of face down. Material from the interstellar medium will get tidally captured and sort of swirl in around the black hole, as we were arguing. Now, even if this material initially starts with some tangled, turbulent velocity and magnetic field, if I rip a tidal tail off of this and stretch it and circularize it and spaghettify it around the black hole, I'm going to stretch those magnetic field lines into this azimuthal or toroidal configuration. And this is pretty unescapable that this should happen, that it should strongly amplify that particular component of the magnetic field. And this is also what we see happening in the simulations. This is the messy version from the simulations where you see this big filamentary flow ripped off of this is the big tidal tail ripping off and eventually circularizing. And these are the magnetic field lines which you see on large scales wrap around and then get wrapped even tighter and tighter and wrapped even tighter and tighter into these spirals. So now let's go back to our picture. So now I've got, I need to come up with a better way of visualizing this. So imagine the field is sort of coming in or out of the board now, right? It's wrapped around in the toroidal direction initially. If this gravity is still going to try and collapse my disk, but as it does so, of course, those field lines are going to get compressed if I squish the disk vertically, and the magnetic pressure is going to build up very quickly and oppose continued vertical collapse of the disk. And it's going to vertically arrest the disk long before it gets to this hyper-thin state, basically. It's going to arrest it while it's still quite puffy. And because it arrests it while it's still quite puffy, it basically guarantees that it can never build up this tremendously large thermal pressure that the other model built up. So it arrests long before it ever gets to the sort of classic disk state, basically, with a high thermal pressure. So here's another movie to illustrate this. So this is showing the colors. I apologize if you have flashing lights bother you. This is all over. But these are showing the magnetic field lines in the lines, and the blue and red show regions where the magnetic field is dominant or subdominant to the thermal pressure. So blue is where the thermal pressure dominates, and red is where the magnetic pressure dominates. And you can see as we finally get close to this accretion disk that the field finally comes into this ordered toroidal configuration where the magnetic fields very strongly dominate the pressure. And just to summarize, I don't have time to walk through all of these things in detail. It turns out this has a tremendous amount of effect on all your predictions. So, what's the difference between a standard disk on the left and one of these disks? We call them flux-frozen disks because of flux freezing being the carrying of magnetic fields that amplifies them here. There's the thermal versus magnetic dominated, but what does that do? Well, I just said one of them is very thin, one of them is quite thick. These magnetically dominated disks are very thick and flared. They cover order 1 of the sky, as seen by the inner black hole. One turns out to be, essentially, the thermal-dominated disks have to be laminar. They have to have sonic turbulent Mach numbers, turbulent velocity over thermal sound speed much less than 1. These flux-frozen disks, because the turbulent velocities almost invariably end up being comparable to the Alfvén speeds of the fluid, end up being highly supersonic. They also have very different cooling times. So the standard disks cool very slowly. These disks cool very fast. That in turn means that the standard disk, there's very different stresses as well, but I should say, sorry, I meant to say this difference here in turn means that the magnetically dominated disks invariably develop multi-phase structure the same way that the interstellar medium does. They basically have to when they're highly turbulent and have very short cooling times. They're unstable to the formation of multi-phase structure, so you get dense clouds and hot gas embedded inside of the disk, all orbiting together. They have much stronger magnetic stresses and magnetic torques that remove angular momentum far more efficiently, which means you can feed the black hole at the same rate for much less mass in the disk, which means it's got very different opacity structure, very different density structure. It also means that it's vastly more gravitationally stable because you need less mass there to fuel the black hole because it's moving so much more quickly, being funneled in very quickly by the magnetic fields, but also because the magnetic fields are stabilizing it themselves. So those dual effects both go in the same direction, and you end up with a difference of like 10 to the 9 in this Toomre Q parameter that's predicted for the disk and its stability. It also completely changes the emission structure because you end up with all the emission coming from a compact, hot, thermalized blackbody region, whereas here you have an extended, cooler region that does most of the emission that's dominated by scattering and reprocessed emission. And again, I could go into much more detail on this, but you can see it in the simulation. So here's a simulation where we don't include magnetic fields, and the inner disk is just this razor-thin thing. And here's where these flux-frozen disks, where you can see it's this huge both multi-phase, turbulent. You can see by eye this has to be turbulent. There's all this structure in the density field, that thick thing that covers most of the sky. It also makes a huge difference, as I mentioned earlier, to the accretion rates. The flux-frozen disk can sustain almost 1,000 times higher accretion rates through to the black hole than these thermal pressure-dominated disks can. The torques and stresses are completely different. I'm just going to skip that. The phase structure is different. As I said earlier, these are some zoom-ins of different phases of the gas. You can see very clearly in this visualization that there's just different scales. But you can see that there's cool, partially ionized gas, warm ionized gas, hot gas at all scales around these black holes. One more movie. This is just visualizing some of the turbulence now versus the thermal pressure and magnetic pressure to give you a little more idea of the multi-phase structure of these disks. So you can see, again, that it's sort of more turbulent dominated or thermal dominated at large scales, but as we zoom in, the magnetic fields really take over in the inner disk, except for little tiny, you'll see little, it might be hard on the screen, sorry. Yeah, it's pretty hard. There are little patches where turbulence dominates, which are reflecting the multi-phase structure. I apologize, in this screen you can't quite see the little patches that appear, little cloudlets and things like that. And there's a paper in progress that relates this in a cartoon way to a lot of these different phenomenology I mentioned earlier, things like what we call the broadline region and the corona and the torus. A lot of these just fall out very naturally from these disks, basically. There's a student, Jaden Bardani, who's doing some explicit radiative transfer calculations on these simulations to show that the disk properties naturally predict things like these broadline emitters that are seen, these dusty regions that are seen. They're all there in these simulations. They're held up above the disk by magnetic pressure, but more importantly, they're not held up, sorry, I shouldn't say they're held up above the disk. They're part of the disk. Everything's just part of the accretion flow, basically. It's all just a multi-phase accretion flow that's very puffy and thick and covers most of the sky. This was just in case, I don't know if Jessica's in the audience, I had one plot to show a work in progress on the IMF in the galactic center in this simulation because I felt like I needed to show it for her. But it's slightly top heavy, but it's sensitive to assumptions. So anyways, I don't have time. I was very overambitious and I had these bonus slides on feedback if I had time to get to them, which I don't. So I'm just gonna skip them. It's obviously something else we're very interested in. And this was just advertising that we're thinking about new physics like how cosmic rays and radiation dust interactions can modify or mediate the energy lost from these black holes as it couples back to the interstellar medium around them. But I'll stop there and thank you all very much.
Thank you, Philip, for a wonderful talk. The floor is open for questions. Yes, over there.
What was the time for Edison accretion? Was it like making this amount of accretion to talk about more, or was it by
Sorry, I couldn't quite hear the question.
how was super Edison?
So in these zoom-ins, I'm just quoting the accretion rate that we measure through different annuli. So technically, the accretion rate I quoted is the accretion rate through the innermost inner boundary condition, which is at, in this simulation, 300 gravitational radii, and the one in prep, 30 gravitational radii, and it's just the actual mass flux rate explicitly through that. So it's not implemented in any, it's just predicted basically there. Some of the calculations I described at the very beginning of my talk, the lower resolution galaxy simulations, before we do this refinement, there, where you're not resolving any of these inflow dynamics, you do have to just put in some prescription for the accretion rate, some analytic model that's a guess or a subgrid scale model for it. And there, we've experimented with various different predictions or scalings that people have proposed in the literature. Once you let it get hyper-Eddington enough, on the large scales, maybe you don't care because it quickly catches up to these high masses, but that's a fair point that we're hoping these newer simulations can inform those models.
How much do these new results affect models of the star formation history in the Milky Way and more generally? For example, does it shift the time when you expect to see star formation happen?
So Sorry, yes. So the question was, how much do these newer models affect the inferences about the star formation history of the Milky Way? For example, when do we expect the peak of star formation or most of the star formation to happen? So I think for the Milky Way specifically, a lot of people think that it's got a relatively small supermassive black hole. So all the black hole AGN stuff we still think is a relatively modest effect, most of us working on this. The point I was making earlier in the talk about this sort of transition from the very bursty period to the calm period, there's been a lot of really interesting work from Gaia in the last couple of years showing that we can really map out this transition in our galaxy and the stellar orbits of low metallicity versus high metallicity stars, and that our galaxy really did appear to undergo this transition from this very chaotic period to this calm period. It appears that the Milky Way underwent that transition quite early, and I think we're still not 100% sure, and when I say quite early, I mean early compared to most of our simulations, for example, that our group has run, but it's a small sample that we've run. So a question is it that our simulations are missing some physics or wrong, or is it that the Milky Way is a bit of an outlier? Others in the field, like Vadim Semenov, has argued fairly compellingly from other larger samples that the Milky Way is probably an outlier, and there's many other hints that we've had for decades that the Milky Way is a bit of an outlier in this respect. So we're actually trying right now to simulate earlier forming galaxies to try and see if we have a better analog to the Milky Way, but it's definitely imprinted there, but I think that's the best I can answer that question right now. It's a very interesting open question.
Okay, a lot of questions. Chungpei, Steve, there.
As you know, the Event Horizon Telescope collaboration, now from their observations, they're favoring magnetically arrested disks in their modeling, but of course their disks are even smaller than yours.
Yeah.
So could you comment on perhaps implications from your
Yeah, so I didn't have time to mention this. So the one exception, I said, the vast majority of work on theoretical modeling of accretion disks, and essentially all of it for quasars, for things accreting at a very high accretion rate, has assumed that the thermal pressure is much larger than the magnetic pressure, but with a couple of exceptions. There's a couple papers, interesting papers that were exceptions, but there's this big exception of these magnetically arrested disks, and this is generally believed to be very low accretion rates, and the two black holes imaged by EHT are very, very low accretion rates relative to Eddington, so opposite end of the spectrum for what we're simulating here. And the idea there is that you have a very strong magnetic field that actually halts accretion. Now, you might wonder, I said it promotes accretion because the magnetic fields torque the gas very efficiently. And actually what this mostly comes down to is the field geometry. So in the arrested disks, you have a primarily poloidal field, and as the flow accretes in, the assumption is that it's a thermal pressure dominated disk at large radii, and then as it pushes in, those field lines get pushed in, and they get packed tighter and tighter around the black hole, and if it's a vertical field, they're gonna just push outwards away, and they're gonna eventually resist accretion. So the key question is really, is the field coming in mostly poloidal or mostly toroidal for which regime you'll end up in? And there's a little bit of work by some of the group at Northwestern with Sasha Tchaikovskoy and collaborators and Bart Ruperta and others, I think with some early experiments that are showing that, but we're trying to simulate some cases that are more in between now motivated by this. We're also interested in exploring the low m-dot regime. Again, this one we purposely picked to be, I historically was biased. I like quasars, so I picked the thing that had the highest accretion rate of all of our simulations to be the first one to do this zoom-in experiment, because I wanted to know how you could fuel something at these enormous rates. But obviously, it's super interesting to repeat this for these low accretion rate systems where we have a lot more data on small scales. Steve?
It looks like in these frozen flux disks that the X-ray emission is far more extended than you would expect for the traditional alpha disk models. So I wonder if that jives with short-term variability in the X-ray emission, which has been observed for a number of AGNs,
Yeah.
as well as redshift and iron K lines, whether you can make them in this kind of
Yeah.
phase.
That's a great question. So the question was, there are some observations from the X-rays of both variability on short time scales and redshifted iron K alpha lines that indicate that a lot of X-ray emission is coming from very close to the horizon. which is interesting in part because it's different from, in the optical, there's all these hints that more of the emission is coming from further out than these older models would have predicted. And it's not obvious by any means if that would follow naturally from this, or this would go the opposite way. As I mentioned, I'm trying to get a student to do some calculations. The problem is also that, this is also part of why we're running even zooming in further, because I mentioned this existing simulation cut off at about 300 gravitational radii, which is too far out to see those effects for the X-rays. So we're trying to go further down. One of the major motivations is to see, do we see a more compact X-ray structure and then maybe some additional diffuse emission or scattering of the X-rays, which would be fine, or do we see only diffuse X-rays, which would be a problem?
Last quick question.
Do these simulations take account into the effects that dark matter and dark energy may have on galaxies, if any?
Yeah, so all of these large-scale simulations include dark matter in the usual approximation of some collisionless cold dark matter species. As I mentioned at the very beginning, this is something that our group has done a lot of work on in other respects, trying to think about astrophysical tests of dark matter. We're running different particle dark matter models where they have different phenomenology on very large scales that could be astrophysically detected. These simulations sort of use the simplest model because we didn't want to, test one hypothesis at a time, I guess was the plan. But and dark energy, in these simulations in these kinds of simulations only appears in the expansion rate of the universe. There's sort of, the cute trick you can do in cosmological simulations is you can basically, especially if dark energy acts like a cosmological constant, you can fold all of that into the expansion rate. All the GR, all the metric terms, et cetera, just get folded into an expansion rate, and then everything else is Newtonian, basically. So that's what we do, which is the usual swindle. If you have a specific dark energy or dark matter model you think would be interesting to model from these kinds of simulations, I'm all ears. But on very small scales, the dark matter density is so low it doesn't really do anything to the dynamics. But on large scales, it's definitely something we're interested in.
Okay, we have other questions, so I encourage everyone to come to the front and speak to our speaker here in a more direct setting. And please join me again in thanking our speaker again for a wonderful talk.
Thank you all.